Hello, everyone. Thanks for joining in with us today. Welcome to today's topic, high voltage bushings, testing with confidence. My name is Michael Fleischer, and I'm the America's Marketing Communications Manager for Megger. I'll be acting as moderator for today's presentation and supporting you on any technical issues or questions with our presenter team. On the left side of your screen, you will see the Ask a Question window. You can submit questions at any time during the presentation, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, your certificate of attendance, copy of the presentation, and link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenter today is Ken Petroff, Business Product Portfolio Manager. To assist with the question and answer session, we also have joining us Joseph Aguirre, Principal Engineer, and Ravi Gupta, Senior Applications Engineer. With that, I will hand things over to Ken. Thanks so much for joining in today, Ken.
Hello, everyone. My name is Ken Petroff, Business Product Portfolio Manager for Megger based in Valley Forge, Pennsylvania. I'm here today to talk about high voltage bushings and how you can test with confidence. A few of the topics that we'll be covering today. First, we'll take a look at Megger and what it has done throughout the past 100+ years when it comes to insulation condition assessment. We'll have a brief introduction to power factor, where we'll talk about some of the basics. We'll go over the different measurement modes that are available and then look at how we do an overall transformer test. Then we'll take a look closer at bushings. We'll see how they're constructed, how they are transported before they are installed to a transformer. And then we'll look at the different high voltage bushing tests that we can do. C1, C2 with inverted C1 and C1 plus C2. Also hot collar, mainly used for lower voltage bushings, but it is a test that can be considered. And then as well as looking at DGA, specifically for oil impregnated paper bushings. We'll then look at a few different case studies where we'll touch on the individual temperature correction, also dielectric frequency response, and 1 Hertz testing in addition to the routine 60 Hertz testing. And then at the end, we'll finally have some time for questions. So first, let's take a look at Megger and its long history with respect to insulation condition assessment of transformers. Starting with what we have out today. For AC insulation, capacitance, and power factor, we have the Delta 4000, the standalone insulation power factor test set. We also have the Trax plus TDX. This will be your multifunction substation tester that has a tan delta add-on. We also have the EDAX, which is our dielectric frequency response test set, which I'll talk a little bit about in later slides. Before that, we did have the Delta 2000 and 3000 preceded by the Alpha 10, and we also had the CB100. And of course, before that, what Megger is well known for is DC insulation resistance, which we've been doing for over 100 years. And why do I bring this up? It's to let you know that Megger has the knowledge and the experience to answer your insulation questions. Next, introducing power factor. For those of you here who are new to the industry or trying to gather some basic information on how power factor is used to evaluate insulation, we first want to start off with some definitions here of what is a dielectric and what is insulation. So the dictionary definition of a dielectric is something that is a poor conductor of electricity. So you would think this would be, silicone, rubber, or wood. Insulation is dielectric material that is used to separate conductors. So this would be, the wood inside of a transformer or the paper that is wrapped around the coils that helps to keep those conductors separated. And it's important to note that the conductors can be at the same potential or different potentials. And then finally, a capacitor is formed when you have a pair of conductors that are separated by a single dielectric. And the most common way to look at that would be to consider a single phase transformer. And here on the left, we have the high voltage winding, and then on the right, we have the low voltage winding. So those two conductors are separated by a single dielectric in the middle, which forms the capacitor that you see here. What's represented here is an ideal system where the current is 100% capacitive and it leads the voltage by exactly 90 degrees. But no insulation is perfect. And what you will see is that there is a certain amount of loss that shows up as resistive current. So then this total current will lead the voltage by a phase angle that's less than 90 degrees. And this is how we determine what the power factor is. And power factor is a calculation. It's the cosine of the phase angle between voltage and current. Ideally, that would be 90 degrees, as explained before. But sometimes you might hear the term tan delta or dissipation factor used when talking about power factor testing. It's the same exact measurement method, but we're looking at a couple different parameters. So for tan delta and dissipation factor, we are looking at the tangent of the phase angle between the watts and the vars. And here, ideally, that phase angle should be 0. And what's important to note about tangent delta or dissipation factor versus power factor is that up to 20%, they are exactly the same. And after 20%, they start to diverge. And anybody who's been doing power factor or dissipation factor will tell you that 20% is clearly in the area that something is catastrophically wrong. So for all intents and purposes, when you're looking at dissipation factor or power factor at levels, between 0 and 2%, then they are going to be almost exactly the same. And using the term tangent delta or dissipation factor versus power factor, it should be understood that, again, those are exactly the same. So why do we perform power factor or dissipation factor tests? It is the most important test of an electrical system for a couple of reasons. The first is to ensure that the paper and the oil doesn't have any contamination. There's no fractures or punctures within that paper insulation. And then also to try to identify when the transformer or bushing is starting to show signs of age. When you can detect the insulation changing over time, that allows you to improve your system. And number one would be for safety. For people working in the general vicinity of the transformer or who live close by, we want to make sure that the insulation is in good condition to prevent any harm from to those people. Next is the efficiency of the assets. With better insulation, your assets will perform better. The lifespan will be increased, which will lead to more uptime and more revenue for your organization. So now that we know why power factor or dissipation factor testing is performed, let's look at when it is performed. Of course, the first place will be during manufacturing. Before any instrument leaves or any bushing or transformer leaves the factory, it's put through a lot of routine tests to ensure compliance to the design and to customer specs. And then once the bushing is received, either a testing company or the utility or the muni co-op will perform commissioning tests. And it's important to note here that commissioning tests for bushings apply to when the bushing is outside of the transformer and then when it is installed. And I'll be discussing that later here in the presentation. The next time when you would perform testing is during routine maintenance. Typically after transformers put into service for the first time, a year later, some tests will be run to make sure that there's no critical changes happening within that first year of life, and then it'll be put on a more time-based or condition-based schedule after that. And then the last reason to test would be during post-fault. So the transformer got kicked out of service, and now you want to understand, did that through current fault, did it potentially impact the insulation within the transformer or the bushings? So you want to perform the power factor and dissipation factor at that time. And what assets benefit from these tests? Of course, transformers, looking at the overall of the windings and of the insulating liquids, again, that's going to be your oil or your FR3. You can also look at surge arresters. And then, of course, what we're here to talk about today is the bushings. But Power factor testing goes beyond just transformers. It can also be used with circuit breakers, rotating machines, cables, and instrument transformers like CTs, PTVTs, and CCVTs. And how is a power factor test performed? You connect your high voltage source to one side, you apply that voltage, you will then measure the current through the capacitor, looking at the capacitive and the resistive components there. And then you make your evaluation of the insulation based on that leakage current that is coming through that capacitor. Now, when we make the connections to bushings, typically you will have a high voltage lead. This will be where if you're doing DFR, you're applying 140 volts or 1400 volts RMS, or if you're using a 10 kV power factor test set, this high voltage lead will provide the source for that 10 kV. You will then have two lower voltage leads. This is what you will typically see as a red or a blue lead. And then finally, the ground connection. It's very important with power factor testing that the instrument itself is at the same ground potential of the asset under test. If you are not at the same ground potential, then any of your grounded or grounded with guard tests will not have proper measurements. I talk about a little bit more of that on the next slide. When it comes to bushings, and for the high voltage bushings that we'll be talking about today, those bushings will come with a tap off the side. And the leads that we have, it allows you to conveniently connect to the bushing tap by disconnecting the big clamp that we have on top that goes to the top of a bushing and using a banana plug to connect onto either the spring or the stud that is within that bushing tap. And we do have a couple unique names when it comes to power factor testing. The first would be the ungrounded specimen test. This is where both terminals are isolated from ground. You then have a grounded specimen test where all of the insulation between the high voltage conductor and ground is measured. And then you can do a grounded specimen test with guard. And this is used to analyze the different components of the grounded specimen test. Since that grounded specimen test includes all of the current coming back on the red, the blue, and the ground, when you guard that out, you can use that as a confirmation of the other tests that you've performed. So if we take another look at this, if we look at the ungrounded specimen test, we have USTR, again, standing for ungrounded specimen test, USTR, USTB, and USTRB. And this means that, with your high voltage lead connected to your asset, you are going to measure the leakage current coming back on the red lead, the blue lead, or both the red and the blue lead. Next, we have the grounded specimen test, the GST-GND. We will be measuring the leakage current that comes back on all three channels, the ground, the red, and the blue. And then finally, the last one is the grounded specimen test with guard. You see that as GST-G and then -R-B or -RB. So in all three of these cases, you will be measuring the current to ground. But when you have guard R, you will not measure the current on the red, but you will measure the current on the blue. The opposite for guard B, where we're guarding out the blue. And then finally guard RB, where we only look at the current that comes back on the ground channel. So very important to keep this in mind as we go through and talk about the next test that we have. Before we hop into the bushings, I do want to just show how these different measurement methods work together when we're talking about the overall transformer test, because if you're testing bushings, then for sure you are going to be testing that transformer as well. So the first test, we see here that we have our high voltage applied to the high side winding, and then we have our red measurement lead connected to the low side of the winding. And in the UST-R mode, we are only going to measure the leakage current that comes back on the red lead. With the GST guard RB, If you remember from the previous slide, when we guard R and B, we're only measuring the current that comes back on the ground channel, and that's shown here by the ammeter being solely on that ground channel there. And then finally, the last measurement, the GST ground, you'll see in this example that the ground path is connected directly to the ammeter along with the red lead. So in this case, we are measuring the sum of USTR, GST guard, RB to give us our GST ground measurement. And when you look at capacitance, you will see these, the first two values for USTR and guard RB, they will add up to the GST ground measurement or fairly close. But if they do not add up, or if you have a question about any of your power factor measurements, whether they're capacitance or power factor itself, you can have a reference to verify that your instrument is working properly. And what we have is an accessory that gives you the field verification capabilities to verify that entire insulation measurement system. Sometimes you may use a capacitor to verify your power factor measurements, but your capacitor is only going to get you your USTR measurements, and it's not going to verify the functionality of that ground channel. And with a device like the PFDF10, you can connect your high voltage, your measure red, and your ground measurements and confirm all aspects of your insulation measurement system. We understand that when you have questionable results, most of the time the blame goes directly onto the instrument that you're using first, and you're always looking for ways to verify that the test set is working properly. And we believe this accessory here can give you that confidence that you need, that the measurements you're getting are correct, and that you can base your asset maintenance decisions off of those measurements from the instrument. So now that we've covered some of the basics of power factor testing, the different test modes, let's talk about bushings, and first starting with their construction. There are a few different bushing types. The majority of what we'll be talking about today is going to be OIP bushings, or oil impregnated paper. This is your typical craft paper, and that is then filled with mineral oil. And the paper is a good insulator, but it is not perfect. There are tiny voids in paper, and so the oil is used to help fill in those voids. The oil is also used to help with convection cooling within a transformer. But when we talk about bushings, not a lot of convection going on, so really that oil is used to fill in the gaps of that craft paper to make the best insulation system that we can have. The next type of bushings, instead of using oil, it's going to use resin. So this is resin impregnated paper. This is where a vacuum is pulled and then resin is pulled into the gaps within the paper itself, and then it's allowed to cure over time, and it creates a similar insulation system. Next, we have resin impregnated synthetic. This is a woven material that is intended to have better heat withstand capabilities than paper itself, but the process is the same as resin impregnated paper, where again, we're not using oil, we're using a resin that's pulled under vacuum, used to fill in the voids in the synthetic material, and then allowed to cure over time. The next technology, and this is mainly used on lower voltage bushings, would be resin bonded paper. This is where the sheet of paper itself has the resin to fill in the voids before it is wrapped around the foil of the bushing. And then finally, we just have cast epoxy bushings, where it's just a very simple process of creating a bushing where you don't need that capacitive grade for the application. So what we'll focus on now is mainly OIP bushings and how they are constructed. Within the center of the bushing, you will have the conductor that runs through, and then this capacitive graded bushing will have layers of insulation and then foil to help break down that voltage before we get to the tap that comes off the side. And the tap is there for a couple of reasons. One is to help determine the health of the bushing, and another one is that if you have a voltage or potential tap, you can use that during bushing monitoring while the transformer's in service, or partial discharge testing, or online measurements. So it's used to get that voltage down to a usable level when it comes to either instruments that are online or offline. And then here is a little bit more detail on how these bushings are constructed. I won't cover every different part of the bushing here today. The part that I really want to focus on is that tap that I'm talking about, that I spent a little bit about talked a little bit about earlier. This tap, it can come in two different flavors, and for low voltage bushings, so these are bushings that are less than 69 kV, this is referred to as a test tap. The reason why it is called a test tap is because it is connected to the last foil in that capacitively graded bushing. And when that is the case, that measurement, when you perform a C2 capacitance measurement, it's going to be an uncontrolled measurement. And what I mean by uncontrolled is that you are measuring the ground from that last layer to the ground flange or the tank of the transformer. And since it is uncontrolled, or the capacitance would change in this way, what you may notice is when you test these bushings, when you have them hanging from a crane, you will see the capacitance measurement change from the time that it is suspended to the time that it's actually installed in a transformer. Again, this is for typically bushings that are less than 69 kV. And then when we get into the higher voltage bushings above 69 kV, this is called a potential tap. And the reason why this is called a potential tap instead of a test tap is because instead of being connected directly to the last layer, the potential tap is connected to the second to last layer, and then the last layer is connected directly to ground. So when you measure the C2 capacitance for a bushing with a potential tap, you will see greater consistency between the uninstalled and the installed capacitance for C2. So for this case, for these type of bushings, we call this a controlled C2 capacitance. So very important to know, whether you're testing low voltage or high voltage bushings, that the tap construction can have a significant impact on the capacitance that's measured while it's suspended before it's installed and then after it is installed. One important consideration for bushings, in particular OIP, is that when they are transported, they will be lying on their side, and that will cause the oil to flow in ways that can impact the measurements of this bushing. So it's important that after receiving a bushing and before you start your commissioning work, that these bushings must be suspended or oriented in a particular way, so that way the oil is doing its job inside the bushing. I do see that there are some transportation requirements for OIP, but I believe it would be a good practice to ensure that the bushings are at a particular angle, greater than, I can't really say I know the exact number, but it should be close to vertical rather than lying down. Also important to note that they should be removed from any wooden crates that they may be stored in. Those wooden crates, if it's hanging or sitting on the ground flange, it may create some external paths to ground, which we want to have avoided. So when you are testing a bushing, please make sure that it is suspended, make sure that it's properly secured, so that way it's not going to fall and hurt anyone or get damaged in the process. But very important that the oil is allowed to recalibrate, readjust, reset itself within the bushing before performing any tests. And now talking about the different bushing tests and the evaluation that we can perform. When you have these high voltage bushings, you will likely have a transformer that has at least a 2-winding transformer where it will have 3 to 4 bushings on the high voltage side, and then 3 to 4 bushings on the low voltage side. And what we'll focus on for right now is just testing a high voltage bushing that's on the primary side. And the connection scheme that I have on the screen now shows that all of the high voltage bushings are shorted together. All of the secondary voltage or all of the secondary bushings are shorted together, and including a extra connection to ground. For whichever winding we're not testing the bushings on, we do want to connect that to ground to remove any possible influence from those bushings. And then what we will do is we will take off the cover of the test tap and we will connect our red measurement lead. Now, it's very important to note that while you are doing bushing tests, you should only have one bushing tap uncovered before you start the test. If you have multiple bushings uncovered and they are just left open and not grounded, when you energize at 10 kV, that means that bushing tap will also see that 10 kV, and it could cause irreparable damage to that bushing. So please, when you are doing your C1 tests, only have one of the bushing taps uncovered and make sure that it is connected to the measurement lead before you start testing. So now that we've hooked up the test set and we've performed a USTR test, we get a result, and now we need to evaluate that. And we have a few different criteria that we can look at for evaluation. First being capacitance. And we want to look at the relative capacitance change. Now, when I say relative, I am talking about the capacitance that is stamped on the bushing nameplate. So if it has changed by greater than or less than 4%, we see this as a reason for that bushing to undergo additional evaluation. Bushings, the way that they're capacitively graded, they should not change over time. So any significant change like this should be investigated immediately for the health and safety of that transformer. Next, we will look at the power factor or dissipation factor change. We will start out by looking at the 60 hertz value, and it's important that the value is corrected to 20 degrees C. And I talk a little bit later about how 20 degrees C temperature correction works. But what we're talking about with this is, again, the relative change. So we look at the bushing nameplate and we see that it has a power factor. And if the change is less than 20%, then we consider that that bushing is in excellent condition and has not aged since the last time or since it was manufactured. A change of up to 50% would be good. A change of up to 100% would be service aged. But any time that that power factor doubles compared to the nameplate would be a reason to investigate. Now, let's say you don't have the nameplate values. You can look at the absolute power factor values at 20 degrees C. So again, if you don't have that nameplate value, then standard practice would be to evaluate the absolute values. And we're looking at 0.5 for excellent, 0.7 for good, 1.0 for aged, and anything above 1% would be cause for additional investigation. And then finally, here at Megger, we do have evaluation of 1 hertz in addition to the 60 hertz. And you'll see that it has the same sort of increase from excellent to good and aged. And then for investigate, we do expect values below 0.2 or above 1.25 to be reason to perform some additional tests on that transformer, or I'm sorry, on that bushing. And later in this presentation, I will talk about what this 1 hertz power factor dissipation factor is. So after you've done the C1 test, your next test will be to perform C2, C1 inverted, and C1 plus C2. You'll see that this connection is very similar to the C1 test, with us swapping where the high voltage lead and the low voltage lead are connected. Now, one important note about this is that when you are doing the C2 tests, you will typically excite at either 500 or 2000 volts. And it's based on, it's going to be bushing by bushing, which one you can use. If you're just going on safety and protecting the asset, then 500 volts is safe to use. And when it comes to power factor and dissipation factor and capacitance, if you test at 500 volts or 2000 volts, you should not see a difference, especially for OIP bushings. If it was a dry type transformer, then yes, you may see the power factor values change as you increase voltage, since there's no oil inside the voids within the paper. So you will get some partial discharge as you increase voltage. But for OIP bushings or transformers, testing at 500 volts or 10,000 volts, you should get the same value if the insulation is in good condition. And then again, the C2 test, we want to only think about those bushings that have the potential tap, where that C2 is controlled. And when we have that, we can then use the same evaluation that we had for C1 to also evaluate the C1 inverse, C2 with test tap, and then also the C1 plus C2 evaluation. And that's what you'll see in the software, that there's only going to be a few settings for evaluating bushing C1, C2, as well as the inverted and then the C1 plus C2. Next, we have the hot collar test. This is where we are not using that test tap on the bottom, and instead we are using a conductive rubber collar that you put around the bushing. And this is used to help separate or test bushings that don't have a test tap, or to test bushings as more as an investigative step, where you can now separate the bushing itself out into different parts by where you place that hot collar strap. And as you see here, with the hot collar strap placed where it is, we can either measure USTR to the red lead, or we can measure GST ground, which would be the red and the green, or we can do GST guard R and just measure the capacitance to ground. So again, it can be very much a diagnostic way of looking at a bushing to try and pinpoint where it may have a failure. And then finally, on the OIP bushings, we do have the ability to take an oil sample and then send that to a lab for DGA analysis, where we look for hydrogen, acetylene, methane, ethane, and ethylene. And now we will start to get into some of the case studies, and first look at temperature correction tables versus individual temperature correction. As I mentioned earlier, when you are testing at 60 hertz power factor, you want to evaluate the results at 20 degrees C. This is because power factor is very temperature dependent. Earlier I said that power factor is not voltage dependent. That is correct, but it is very correct as well to say that power factor is temperature dependent. And if you're testing in the winter time and then you go and test in the summertime, you may see drastically different values of your power factor. What is common practice today is to use temperature correction tables to get you from one temperature back to 20 degrees C. But if you read through the standards, it notes that no single correction curve will fit all cases. And it makes sense that this statement is in the standard, because the temperature correction tables come from manufacturers of bushings. And when they are manufacturing these bushings, they are in the best possible insulation condition that they will ever be. And they determine temperature correction tables based on these bushings that are in ideal condition. So correction tables will work if your bushing is in ideal condition. But insulation power factor never improves from the time that the bushing leaves the factory. So it's always going to get worse. And if we know that it's always going to get worse, then we know that the temperature correction tables won't necessarily work for all cases. But it is the standard practice today, so we correct with the tables, and then we look at the limits set by the standards, which you saw on the previous slide. But there is a lot of doubt when readings are not as expected. So whether the value is a little bit higher or a little bit lower than the previous time, it's difficult to make conclusions on that. So what a lot of customers do is they will trend power factor data over time. But as I mentioned before, when we look at this graph of a transformer from high to low, we see that the power factor comes down from its initial highs in 1973 down to 1993, decreasing by almost 0.15% power factor. And if we know that insulation never improves, then what would be the cause for this seemingly improvement in power factor over time? And I think that it could only be contributed to incorrect temperature recorded at the time or incorrect temperature corrections used at the time. So when we see this trending graph, it still doesn't answer a lot of questions for us. We can't say that the bouncing around that it's done at the end is really indicative of the bushing getting that much worse. And the main thing to note when we do power factor testing at 60 hertz is that early deterioration is not noticeable. The values will change very small from a good or an excellent to a good to an aged bushing. And it's really only with other methods can we start to see these bushings change before it would show up at 60 hertz, and more on that later. So temperature correction tables, what I have here are a couple bushing results. The first test, we see that corrected to 20 degrees C, we have a value of 0.51. It has not changed too significantly, and yeah, it's a little aged from the nameplate values. But then the second bushing result, we see that the at 20 degrees C is quite a bit higher, almost 3 times higher. The difference in power factor from 20 degrees C is quite a bit, and it's being recommended that this bushing be investigated. So looking at these two bushings, which one would we say is the one that requires more maintenance efforts? And I think we would all agree that it's the second bushing. But it turns out that these bushings are actually the same 69 kV bushing. So what is different? The only thing that was different is the temperature at which the bushing was when the test was performed. One was around 10 degrees C and the other was around 22 degrees. So what can we do? If we know that temperature correction tables don't work when bushing insulation starts to deteriorate, is there another option for us? And that other option is called the individual temperature correction. And this comes from the C57.12.200, where it is called the Arrhenius equation. And Arrhenius was a guy back in the 1800s who found out that there's a relationship between temperature and frequency. And when we use that information, what we find is that for a given temperature, say if we're testing outside and it's 30 degrees C, we know that there is a frequency that we can measure at that corresponds to the 20 degrees C measurement. So instead of measuring at just 60 hertz, we might measure at 60 and 150 hertz. And that will give us our hot temperature correction. If we're testing at 10 degrees C and we want to get back to 20 degrees C, then we would measure at, say, 30 hertz. And that would be the 20 degrees C measurement. So here, when we apply this to that same bushing, and when we tested at either 5 degrees C or 45 degrees C, we notice that using this Arrhenius equation or individual temperature correction method, it gets us a lot closer in values than when we use the temperature correction tables. So just know that there is a better way to perform temperature correction, and it is called the Arrhenius equation, or the individual temperature correction, here at Megger. And this will allow you to make the best informed maintenance decisions for your assets. Next, we want to look at some advanced tests. The first being dielectric frequency response, and then how 1 Hertz power factor fits into this. So earlier, I talked that when you change voltage, your power factor should not change, and that is correct. When you change temperature, your power factor should change. That is correct as well. And the last truth about insulation, and I'm sure there's more to come many years after this, but the one that we focus on today is that when you change frequency, power factor also changes. And dielectric frequency response is looking at insulation from down to 0.1 millihertz up to 1000 hertz. And when we do that, we can take our measured power factor plot and we can compare that to a model. And for a bushing, that model is going to be how the oil and the paper inside relate to one another. They call this the XY geometry. And if we know that approximate geometry, we can compare that to our measured values. And when we do that, we can determine the moisture that is within the solid insulation, so the paper in bushings or the paper in the spacers and barriers within transformers. And then we can also determine the conductivity of the oil. So with this DFR method, we can truly understand the state of the bushing or whatever asset that we're testing. And if I'm being truthful, all power factor testing should be done with dielectric frequency response. It is simply the #1 way to understand what is going on with your asset. The one caveat to that is that dielectric frequency response testing can take a long time. For each bushing, maybe 15 to 20 minutes at 20 degrees C. When you get a lot colder, it could be 40 minutes. So if we know that testing DFR is going to take a long time, and we don't necessarily want to test all of our good insulation, we want to figure out which insulation is starting to deteriorate. What we have found is that instead of using this entire dielectric frequency response range, we can hone in on the 1 Hertz value. And the 1 Hertz can tell us a little bit of information. And when we look at 1 Hertz, what we can do is, using the same connection that you're already using today for your 10 kV 60 Hertz power factor, we can also perform the 1 Hertz test. And our software today is automatically configured to run 1 Hertz and also run ITC. And what we see is that with the 1 Hertz value, we can validate your expected line frequency 60 Hertz results. Also, when your 60 Hertz results are changing, maybe they're a little bit lower or higher than you measured last time, 1 Hertz can also be used to confirm these questionable results. And then finally, 1 Hertz can detect problems when line frequency looks acceptable. And why does 1 Hertz work? Well, it works because the resistive current is exaggerated at this lower frequency. So it makes up more of the total current than you would see at 60 Hertz. And then finally, if we look at the application of moisture that comes from C57.161 in 2018, it says that there are a few variable and fixed parameters within an insulation system. What is normally fixed will be the temperature. And no, this does not mean that the transformer or bushing stays at one steady temperature during operation. This means that during your testing, that bushing is not going to change temperature significantly. If it's 18 degrees C out, then in another minute when the test completes, it's still going to be 18 degrees C. And what's normally fixed or variable within limits, that's going to be that paper and the oil inside the OIP, those geometry parameters, normally those are pretty standard for sister bushings. That's not going to change. And then in addition to that, the geometrical capacitance. So if you look at the capacitance within the transformer or the bushing, I should say, it's not going to change over time if there has been no degradation. So then finally, what we're left with is that the only thing that can change within the system is going to be the liquid insulation conductivity and the moisture in the solid insulation. Because we know that during the test, the temperature of the bushing is not going to change. We know that the capacitance and the XY geometry inside is not going to change over those couple of minutes. So the only thing that could have changed from the previous time is degradation of the insulation. And again, being that liquid or solid insulation. And then if we take a look at the effect of just moisture coming from that same standard we were talking about before, here we have a few different curves here for different levels of moisture. And we see that the difference, if we look between 0, 1, and 2% moisture, that it doesn't have a very big impact on that 60 hertz measurement. But as we go lower down to 1 hertz, we can see that for a bushing or a transformer with 4% moisture, the impact at the 1 hertz measurement is almost 10 times higher than it is at 60 hertz. So certainly when you talk about, say, 1% moisture, that impact is quite significant. The sort of magnifying glass that you have on the developing problem with 1 hertz compared to what you would see at 60 hertz. So now looking at our next case study here for this 69 kV bushings. This customer, they were going out, they were performing some routine maintenance on a transformer, and what they saw is that 2 out of the 3 bushings were looking good, and they had 1 that was aged. And aged with the ITC correction, 0.65. Is it a little high? Yes. But is it something that would jump out and scream investigate? You can tell me. You're the ones who have been in the field more than me. But I think in talking with customers, if this was all the information that they had to go on, they might have said, well, you know what, these bushings are, yes, it's changed, but it might be in good enough condition to put it back into service. But what the customer was able to do is also perform the test at 1 hertz. And what they saw was 2 things. The first being that for the 2 bushings that measured good at 60 hertz, they were also measuring good at 1 hertz. So the 1 hertz, without trending, without having to have a database, this confirmed that those first 2 bushings were in fact in good condition. The next thing that they saw was that the 3rd bushing clearly indicated a change in the insulation system for that H3 bushing. And those losses that were seen at 60 hertz were amplified down at 1 hertz. So 1 hertz enabled this particular customer to determine that 2 of the bushings were good, confirmed that they were good with 1 hertz, and then found that the 1 bushing was bad, and then confirmed with this extremely high 1 hertz power factor value. And for this transformer, and for many other transformers like it, when it has 3 bushings on the high side, they are typically the same bushing type from the same manufacturer that was built in the same year with the same kVA, with the same amp rating. So you would expect that these bushings will age similarly as time goes on. And any changes that are seen in 1 bushing compared to the other 2 is likely due to that insulation changing inside. So then, this customer determined that yes, this bushing needs to come out immediately. This transformer is at, risk of failing due to this bushing. So they replaced the H3, and what they saw is that the 60 hertz and the 1 hertz of this new bushing that was put into place, they were also good. So again, using that information from the first 3 tests, seeing that they had 2 good bushings, they also measured low at 1 hertz, and they saw with this new bushing after it was installed that it was low at 60 hertz and low at 1 hertz. So some conclusions from this. With the 1 Hertz, it helps confirm your expected 60 Hertz power factor, and it detects early and advanced degradation of insulation. So again, looking at that third bushing and how it changed significantly at 1 Hertz compared to its sister bushings. And then this transformer was able to be put back into service with extended life, and that these table correction factors are not applicable to 1 Hertz. I didn't really mention it previously, but when you are correcting the 1 Hertz, you have to use ITC. There is no other way, because those temperature correction tables only exist and are only applicable to 50 and 60 Hertz. Next, we have a case study on some 69 kV RAP bushings. This particular customer, they received some bushings, and they noticed that immediately the crates were damaged. And whenever you notice that your equipment comes in with damaged crates, you get that pit feeling in your stomach that something could be further wrong. Either they're damaged, or in this case, when they opened up the crates, they saw that the wrapper was torn and that there was water inside the wrapping and in contact with the bushings. So immediately alarms are going off. They have to start their commissioning tests. And what they found for 2 particular bushings that we're focusing on out of the 9 that they tested is that they had 1 bushing that measured good at 60 Hertz, and it also measured good at 1 Hertz. And then another bushing that measured high at 60 Hertz, and then also measured high at 1 Hertz. So again, using this 1 Hertz in 2 different ways to confirm good 60 Hertz power factor measurements and to confirm bad 60 Hertz power factor measurements. And then finally, this customer wanted to take this testing 1 step further. And this brings us back to the dielectric frequency response, where if you were going to implement DFR into your test routine, one of the best ways to do that to really maximize your team's productivity is to perform 60 Hertz testing along with 1 Hertz testing, since it's the same machine, same connection, software already configured to do those additional tests. And then when you think that you have an issue, say where the 1 Hertz is higher than expected, then you could bring out the full dielectric frequency response instrument and confirm your analysis. And absolutely what they found with these RIP bushings is that they tested the bushing that was good at 60 and 1 Hertz and saw that the moisture was as new. And then for that bushing that had the torn wrapping with the water inside touching the bushing, it certainly had high moisture. So when you think about the different tests and how you can really make the most of the technology that's available today, it's important to consider that really 3-step process of testing insulation at 10 kV 60 Hertz, 1 Hertz, and then DFR to pinpoint where the issues are. And the last case study is looking at dissolved gas analysis in 1 Hertz, and how can that help us better understand the state of bushings. This particular customer, back in 2016, this was written up that they had these extra high voltage bushings, 735 kV, and since 2012, they had replaced some bushings because they were experiencing a lot of failures originally. So new bushings were created specifically for this customer, and they replaced 3 of them, and they replaced 45, and out of that, 3 of them failed, causing major explosions and damages within a substation. This particular customer had to set up a security radius to keep all people out until the root cause of these failures were declared to be absolutely known. The bushing manufacturer was then contacted to do some additional tests, and this is what they found. The first thing that they did was DFR sweep on the bushings, but I want to focus solely on the 1 Hertz. And when we look at the 1 Hertz, we saw that 2 of these bushings had high 1 hertz. So this would be 1 hertz above 1% power factor at 20 degrees C. Then when we look at the DGA examples, we see that where there was high 1 hertz values and high DGA levels for hydrogen, acetylene, methane, and ethane, they correlated very nicely to one another. And since these two bushings showed some potential risk of failure, they were then deconstructed, and what they found inside was that one of the byproducts, from having this oil and paper inside is you get this X-wax, and it was found on the innermost layer of these extra high voltage bushings. So this corresponded directly to the DGA and the 1 hertz measurements that were made before. So whether you are performing C1, C2, C1 inverse, C1 plus C2, make sure to look at those 1 hertz values. And if you have OIP bushings and you're taking oil samples, you can use those to start to correlate them back to one another to try and confirm what these problems are. We are steadfast in our belief that with more information, you can make better informed decisions. And that's what we're trying to bring here today, talking about, looking beyond just the 60 hertz power factor. What else can be found with this individual temperature correction using the Arrhenius equation? What can be found with 1 hertz? And what decisions or conclusions can you make when you look at the full dielectric frequency response of an insulation system? So coming to some conclusions here, first of all, when we look at 60 hertz power factor, you are going to do the 10 kV 60 hertz power factor. I am not here to try and convince you to stop doing this. People have been doing it for decades and they will continue to do that. But what we do recommend is that you need to go a little bit beyond the 10 kV 60 hertz because it is very insensitive to developing changes in the insulation. And if you are using temperature correction tables, please keep in mind that these do not consider how that insulation has changed over time. They're really only meant for bushings or transformers that are in ideal condition, almost directly from the factory. And then trending at 60 hertz, it might not always be available. And then again, why would you want to draw conclusions from these results that were corrected to 20 degrees C, potentially using these incorrect temperature correction tables? Then lastly, you do have the option of comparing your 60 hertz values to a proprietary database. Typically, these do come with a high membership cost, but then you also have to question how were these results temperature corrected? If these results in this proprietary database were not taken into account the unique aging of that insulation system, then they may not apply to that particular bushing that you're trying to evaluate. So what we do recommend is to perform that 1 hertz power factor test, again, using that same connection as your 60 hertz power factor test, using the same connection with software that's already pre-configured to do that, and it will give you immediate confirmation of your 60 hertz measurement without any trending required. Of course, you can still do the trending, but this method will get you the best immediate insulation condition assessment for your bushings. To again, validate when 60 hertz measurements look good, confirm when 60 hertz measurements are questionable, and also to detect early signs of insulation changing. And we know right now, the way that it is with supply chain, it's much better to get a bushing on order now and have a long lead time than have to place an order for an immediate delivery and you end up paying through the nose for that. So, trying to, take all of this into consideration so you can make the best informed decisions you can about your maintenance activities. And as I mentioned before, we are recommending a 3-step insulation evaluation process. You're going to do your high voltage 60 hertz power factor. You're going to take that 10 kV measurement and you're going to correct to 20 degrees C using ITC measurements. You're also going to look at the 1 Hertz. This is a lower voltage test, and again, reducing voltage should not change your power factor measurement for OIP systems. And then you will correct that 1 Hertz value back to 20 degrees C using the ITC method, and that will help you determine where you may want to look for that conclusive analysis with your DFR, where you're looking from 0.1 millihertz all the way up to 1000 hertz. And that brings me to the end of my presentation today. Thank you very much to everyone who joined in and got to learn a little bit more about how to test your high voltage bushings with confidence. Thank you.
All right, thanks a lot, Ken. We're going to take a few minutes and take some of the questions that we've received during the presentation. If you have any questions, please submit them now into the Ask a Question window. For those of you who are heading out, please be sure to fill out that survey over there on the bottom row there, or if it's popped up on the screen for you. We greatly appreciate to hear what you thought of our webinar today and how we can continue to improve upon our series. On that survey, there's also a field for you to request a quote or a demo on any of the Mega products we talked about today. As a quick reminder, a copy of the presentation, a certificate of attendance, and a link to the video recording of this webinar will be emailed to everyone in about 2 business days, if not before. Additionally, the link that you used to join today will become a recording link in about 2 hours after the system has processed our recording. If you'd like to join us in person later this year to discuss innovations and advancements in power transformers, you can check out Mega Power Grid Summit 2024 in the banner at the bottom of the screen or at megapowergrid.com. You can also view video recordings of previous webinars as well as register for upcoming webinars on our website at megger.com/webinars. Be sure to register for our upcoming webinar on August 16th titled Cracking the Code, High Voltage Circuit Breakers, which will be presented by Brett Kersey. All right, so let's jump into some questions while I find that over here. So our first one we're sending over to our colleague, Joseph Aguirre. Joseph, just want to ensure I'm on the same page. Is the tap also the C2 connection?
Yes. So if you're talking about a test tap, a potential tap, these are all referring to the C2 tap as well. So depending on where you work in the business, so everybody has their own terminologies that they use when testing. So if your bushing is a high voltage bushing, usually about 12.5 kV or above, and when I say 12.5, that is just showing that it's medium voltage wise. On these larger power transformers, you typically will have a test tap, potential tap, or a C2 tap. Like I said, it all depends on your terminology, how you want to use it. And that's where you're going to make your C2 test. And the C2 test is basically using your high voltage lead on that test tap. And then you'll have your red measurement lead on the top of the bushing. And if you do not have any of those taps, because even some of these larger power transformer bushings does not have a test tap like that, then that's when you're going to use your hot collar.
Throwing things over to Ravi Gupta. Hey, Ravi, I have a request for a C3 test. Is that basically a C1 and C2 test?
No, well, typically not. So usually the C3 term comes up when the bushing is greater than 69 kV. And as Ken was explaining in one of his slides, what usually happens is, the bushing is a series of capacitors, about 20, 25, something like that. And typically your last capacitor is your C2, and the rest of them are just considered C1. So your overall bushing is C1 plus C2. However, for bushings that are greater than 69 kV, your second last capacitor is your C2, and your last capacitor is also grounded. It's technically in parallel with your C2 because your C2 is grounded, or your second last capacitor is grounded, and your last capacitor is grounded. So they are just in parallel. And that particular tap is considered as C3. The reason we have this capacitance is also because if you have monitoring devices for your bushing, they kind of use that voltage divider form between your second last capacitance and last capacitance, and that is what is being measured, and that's how we are monitoring the bushing condition.
Thanks, Ravi. Our next question is going back over to Joe. Joe, how long should the bushing be vertical prior to testing?
So there's a industry general rule of thumb of about 24 hours. And this can vary depending on the length or size of your bushing, depending on the voltage level. And the reason why you want to maintain that it's vertical is because sometimes you can get some trapped air bubbles within that oil, which can kind of bring down that dielectric strength. So you want it to kind of return or kind of burp out of that oil, and that's why you want to put it vertically. So when I was in the field, sometimes we'd stand it up for, 10, 15 minutes to test, pretty fine. But like I said before, the general rule of thumb is about 24 hours of having it standing upright vertical.
Thanks, Joe. Next question is going back over to Ravi. Ravi, which standards could be used for evaluation of results?
So when we talk about regular power factor, that is your C57.12.90, and that covers your winding resistance, turns ratio, a lot of different tests that go about in the field for anything that is power transformer, and that includes power factor. There is one more standard, which is not really a standard, it's more of a guide, and that is C50161, and that has to do with the DFR. We have a few more questions about it, so I'll cover DFR when we do talk about that. But usually this is about power factor testing, but we go from 1 millihertz to 1000 hertz.
All right, next question's over to Joe. What can cause a negative PF on a bushing mounted in transformer?
So the general thought is whenever you're talking about power factor, you're looking at any kind of leakage current that's coming off of the transformer, right? And or bushing or apparatus that you're testing. So what that means is you're generating more power than what you're putting in. So therefore, typically, if you have a negative, there's some sort of circulating current inside of your transformer apparatus. That's typically due to not having a proper ground. So sometimes you might have a transformer that's sitting there, it's probably new, and once you've connected all the bushings and everything, and you're testing your different tests, you might start with C1, C2s first, and you may not have a physical ground on your transformer. Or it might be in a temporary state where you have a drive ground. So that drive ground's not physically deep enough to get a good ground connection. These are what usually causes any kind of negative power factor, whether it's on an overall test or on a C1, C2.
Thanks, Joe. Back over to Ravi. What is tip-up tan delta value? Is it significant in testing of bushing and transformer winding?
Okay, so we'll talk a little bit about tip-up test as to what it is. So when we do talk about regular power factor testing, your C1 testing, it is done at about 10 kV. And those are the results that we are getting. And when we do 1 hertz testing, it's typically done at about 250 volts. Your tip-up test is usually when it's more used on overall testing, but what we're trying to see is, okay, so my transformer is failing at 10 kV. So let me try to do a tip-up test at multiple voltages. So we'll do it at 2, 4, 6, 8, and 10. And then we'll try to see at which voltage is my transformers or my power factor increasing. Typically, your power factor is not voltage dependent. So whether you do it at a lower voltage, higher voltage, it's going to be the exact same value. Tip-up test is the next step if you have bad power factor values to try and investigate as to where that value could be. Whenever we talk about bushings, especially C1, C2 test, the thing to note there is that your C1 test is always done at 10 kV because the bushings are at much higher voltages. So a tip-up test is not as significant when we are trying to evaluate a bushing if it is failing the 10 kV at that point.
Thanks, Ravi. Back over to Joe. If we detect gases on a transformer and electrical tests don't reveal any defect, could this come from gases in a bushing?
More than likely not. So whenever you're talking about oil impregnated bushings, the bushings themselves have oil that is separate from the transformer. So inside the actual bushing housing itself, you're going to have paper and oil to help strengthen the insulated medium of the bushing itself, right? And then you have a center conductor that goes in there that allows the voltage to pass through the bushing to the transformer. So that bushing oil should be separate from your transformer oil, right? And if you are having some kind of erroneous gases, I would say look at your Duval triangle and run some DGA measurements to see kind of what these different gases are. And then from there, you may have to drain the oil and do an internal inspection to see if there's not anything that could be damaged inside of your transformer physically that's not yet showing on your testing. And it all depends on what kind of testing that you're doing. If you're only performing power factor testing, that's not the whole picture. You need to have multiple different tests, TTR, winding resistance, SFRA. You could do frequency stray losses. You could do leakage reactance tests. There's many of other testing that you can perform on your transformer. And you have to have multiple questionable results, and those kind of guide you to where these deficiencies are in the transformer.
Thanks, Joe. Back over to Ravi. Does the 1 Hertz test also apply to transformer overall tests?
Okay, so the short answer is yes. And well, the long answer is, so we didn't show a lot of case studies in this particular presentation. But hopefully when we have something about power factor in the future, we will include the case studies on overall transformer as well. But yes, and there's a dedicated website as well. So if you just type 1 Hertz testing /Megger, you'll be able to find something. But the idea of 1 Hertz is that at 60 Hertz, we can have results that can be either questionable, just on the line, or failing, or sometimes even passing, yeah. But the 1 Hertz, because the sensitivity is a lot more, one of my favorite case studies is where it is a brand new transformer and it is an acceptance test or a commission test that they're doing. And what they were able to find was there was very high amount of moisture in the transformer, but everything in 60 Hertz was great. All those values were lower than 0.2 for a brand new transformer. That is great. So it passed that, but in 1 Hertz, those values were around 1%. And that was concerning because it was a brand new transformer. Technically, it was not failing, but it was, relatively very high. So once we did further investigation, the oil was sent to 2 different labs. And then they also did DFR, which confirmed the same thing. But then we were able to find out that, okay, the moisture was actually more than 15, 16 ppm. And that is something that we would have missed if we just did the regular 60 Hertz power factor.
Thanks, Ravi. Over to Joe. What is the drawback of 1 Hertz PF measurement? Why is it not performed as a first measurement?
So the reason why you can't just run around and just only perform 1 Hertz is kind of what I'm gathering as this, and then do a 60 Hertz as a secondary. The reason for this is because the standards as far as pass-fail criteria, when you're going to take the transformer out of service or place it back into service, all of these standards are wrote around the 60 Hertz power frequency measurement, right? So the 1 Hertz is all it's doing is giving you a pre-indication of what's going to happen at 60 Hertz, basically giving you a larger resolution so you can see these deficiencies or insulation degradation happening before they reach that 60 Hertz frequency. So this allows you more time, especially with some of Ken's case studies that he was showing on there, where the lead time for some of these bushings might be 18 months to 2 years out, where if you see it's elevating at your 1 Hertz, now you can go ahead and purchase this, maybe get this off an O&M job, put this on a capital budget, and now order a new bushing, kind of babysit that transformer. And when I mean babysit it, maybe not put it on full load, or do more periodic testing versus your 5, 7, 10-year maintenance schedules to see if that power factor is creeping up higher at that 1 Hertz. That way you can know not to put as much load, to add some more load in the field until that bushing comes in. So the 1 hertz is not a standard. It is part of a guideline that is part of IEEE, but the pass-fail standard is 60 hertz. That's why you perform it first. There is the only drawback of doing a 1 hertz measurement is you're holding the physical test button down for additional 1 minute. Other than that, there is no significant drawbacks. You actually gain more information from it. Like I said, because it broadens your resolution and gives you higher visibility of what that transformer or your bushing is acting, because it lengthens that resistive current.
Joe, over to Ravi. When performing sweep frequency test, I got 3 curves with a good shape, but one of them is shifted up. Comparing to the 2 others, is it good or bad even if it has the same shape?
Okay, so this is a completely different test. It is the SFRA test, but I'll talk a little bit about it. So when you are doing SFRA, all you're trying to do, what the test is you inject voltage and you're measuring voltage, and then you're representing in terms of decibels or ratio. And what you're trying to look for is, has there been any mechanical movement inside the whole transformer? And if it is, depending on if it's at a lower frequency or higher frequencies, you can think about, the lower frequencies are core movements, whereas the higher frequencies, you go outwards from the core. So it's windings, and then you finally go to bushings. And if you have 3 curves, so it'll then depend if it's just phase A, phase B, phase C, like what are those 3 curves and where you're looking for that change. But typically, if you have it at lower frequency, if the transformer was magnetized for some reason, the whole curve will shift either up or down, just because of the core magnetization. But then again, like the whole shift, it depends on which frequency range are you looking at, and then we can make more assessments. So with the data that I have, this is all the information that I can give right now.
Thanks, Ravi. Over to Joe. How long does it take to perform a 60 hertz test for 3 winding 230 kV transformer? Does it take the same amount of time for a 1 hertz test?
So just like I was saying before, if you utilize our technology, you're already running the 60 hertz test. You already have the button down. So for each of the 3 tests like Ravi identified before, so on the overall test, you're only going to run additional 1 minute 3 times. That would be on the CHG test, or the capacitance high to ground, the CHL test was capacitance high to low, and the CLG test. So whenever you're talking about overall testing for that 1 hertz, you're doing an additional 3 minutes. And then whenever you're performing it for each bushing, that all varies depending on how many bushings you have. So if you have a 3 winding transformer, so I'm assuming it's probably a YY delta with a shared HOXO. So that kind of eliminates one of the bushings as well. So then you would have 4, 7, 10 bushings that you test. So additionally, it'll be about a full additional 13 minutes of holding the button down.
Joseph, over to Ravi. Why is 10 delta measured in related frequency?
Rated frequency, yes.
Sorry, rated frequency.
Yeah, that's fine. So tan delta or power factor, similar things. It's just, ratio of different angles, so almost the same value up to about 15%. And typically it's always done at rated frequency. The reason for that is a little bit of the history. So if we talk about power factor testing began about 102, 103 years ago. And at that time, like, because we were making it for, the transformer is made for rated frequency, that was what was used. And there's a history about the 10 kV that we use as well. So earlier we didn't have good ways to fight against noise, and there was always some noise that you had when you were trying to take the measurement. So you would always, just keep increasing the voltage, so the percentage that the noise is affecting is smaller. And conventionally, the power factor was done at 10 kV. And if you're talking about America, 60 hertz. Over time, we realized that, okay, whenever we are doing it at 60 hertz, we are having issues with noise. So what if we slightly change our frequency? So every manufacturer that is making a test set right now does not really do it at line frequency. We say that we do it at line frequency, but what we do is we do it at 57 hertz and 63 hertz or 64 hertz, and then we take the average of that too. And the only reason we have those 2 different frequencies is because all your noise or all your harmonics are going to be in multiples of 60. And that's how we beat that. So typically, if we right now do power factor at even 250 volts or 100 volts, you will get the exact same value. But because the standard dictates to do it at 10 kV, we do it at 10 kV, and then those two frequencies, and we take an average and we call it a day.
Thanks, Ravi. Over to Joseph. Can you clarify ITC for different frequencies?
Yes. So as Ken was saying, that temperature and frequencies they have a direct correlation to each other. So if you just have a frequency band and or if you're monitoring frequency at different temperatures, it behaves in a certain way via the irradiance equation. So if temperature increases, depending on what power factor you're looking for, that power factor or frequency would increase proportionally. So whenever you're talking about ITC, you want to correct at 20 degrees C. So there is a unique frequency algorithm that we have, so we can plot exactly where it is depending on temperature for that unique frequency to test back to. So you also have your ambient temperature that you're going to test, and that's going to have its own frequency pattern as well. So whenever you're testing, you're looking at ambient temperature, your corrected temperature, and then your asset temperature. And from that point on, you're kind of doing a triple verification because the frequency is not going to lie. And as you're testing it, you're going to get relatively the same power factor of all those frequencies, right? And that's going to give you your true power factor reading.
Thanks, Joseph. Over to Ravi. When testing, how many readings are required?
Okay, so I'll start with the bushings. When you think about power factor testing, there's a lot of different things that are done, as I answered in the previous question, to make sure that those readings are not impacted by noise, that all the power that the power factor test set is outputting, it is being received at the other end, whether it's through ground or any other lead. So only one reading is required. So if you talk about C1 testing, you only need one C1 results for all your different bushings, H0, H1, H2, H3, and your X side. And when you talk about the overall power factor testing, then it changes. So you have injection from the high voltage side, and then you're measuring on the low voltage and the ground. So you have a couple of different modes like UST, then GST, and then GST guard. But all that means is you have three different capacitance in your transformer that you want to measure. And where do these three capacitance come from? So think about the voltages. So we have one high side voltage, one low side voltage, which are different voltage, and the other is ground, which is at 0. So now we have three different potentials, so three capacitors between them. So ideally what we're trying to measure is your CHL, CHG, and your CLG. So those are the things that we're trying to measure, and then we inject from the low side, and it's a parity so that we get CHL again to make sure that it's the exact same value. So we only run power factor once, but there are different modes or different capacitance that we are measuring. And those three tests that I talked about when you're injecting from the high side, those three different modes, again, you get results for all three. You can do single test, but you get results for all three. So it's technically one test, and you get those three results. But hopefully I was able to clarify a little bit more. Thanks.
Thanks, Ravi. Over to Joe. While performing the hot collar test, the diagram showed that connection being close to the high voltage lead compared to the test tap located close to the base of the bushing. Where do you place the hot collar test lead on the bushing? Does it matter?
Yes, it does, and it depends on the length of your bushing. So if you're talking about power transformers and the skirt count, let's say, is like 12, right? That is far enough from your phase to ground, because whenever I'm saying phase to ground, I just mean your high voltage lead, and your high voltage lead is actually going to go directly onto your hot collar, right? So you're going to wrap it around there, and typically what you want to go is 3 skirts down from the bushing that you're testing as far as the high voltage or EHV bushings, and then you would apply your voltage. However, if you're doing something like on a smaller unit, like a pad mount or something like that, where you only have 3 skirts, you'll have to try to put it as far up as possible. If not, then you'll have a lot of tracking, because at this point, you're just really looking at voltage tracking back to ground whenever you're utilizing a hot collar test, because there's no way to test the C2 portion.
Thanks, Joe. And I'm going to keep this next question with you as well. What is the difference between IDAX and SFRA?
I'm glad you asked because a lot of people kind of misconstrue or kind of think that they're the same test. These are two totally different tests that look at two totally different things on your transformer. So whenever you talk about DFR, that is a dielectric frequency response. So we're actually looking at the insulating medium on your transformer. So that is your oil and your paper on your transformer. And so you're looking more at a power factor and how the insulation is degrading or having some moisture ingress on the actual paper insulation or oil, right? Whenever you're talking about a SFRA test, that's a sweep frequency response analysis. That is a mechanical. So you're looking at physical changes that happen in the transformer. So if you had any hoop buckling or loose connections or any kind of shifts within the transformer or core, you would see these physical changes where whenever you talk about DFR, we're looking at insulation changes as far as power factor.
And if I could add one more thing, so whenever we are doing SFRA, we are usually just injecting voltage, and typically it's lower voltage, about 12 volts, 24 volts, and we are measuring voltage on the other side. So it's a ratio of those voltages. Whenever we are talking about DFR, or it's just power factor over a wide frequency. So again, it's graphs, but in the end, what we are doing is we are applying voltage, but we are taking ratios of current, and that is your resistive current and your capacitive current, the angle between the total current and your resistive current. Thanks.
Thank you, Ravi, and thank you, Joe, for being available for the Q&A. I think at this point we've run out of time to continue our Q&A run here. We have about a dozen other questions that were brought up, as this is a very beefy topic. So if you'd like to reach out to us directly or follow with us offline, please do so at broadcast@megger.com or TSG for our technical support group at megger.com. You can also reach out to us on the survey at the end of this webinar when it concludes and request a quote or a demo on any of the information that we ran over through here. But as a reminder, I'd like to keep everyone aware that the presentation will be sent out along with your certificate of attendance and a link to rewatch this webinar in about 2 business days, but I'll try and have it out a little bit earlier than that. But ultimately, I'd like to thank you all for attending today. After we conclude here, please do feel free to fill out that survey. Let us know how we did, how we can continue to improve upon this, or any topics you'd like us to cover in the future. But ultimately, I hope you all have a great weekend, and thanks again for joining us today. And thanks again for our wonderful panelists for answering as many questions as we had time for. But with that, I hope to see you guys at our next webinar, and have a great weekend.